Morning, everyone. I have a note from... Okay. When you run out of a room, you have to grab the person in front of you. It's a rule. Okay. I have a note from Fahad saying GitHub appears to be down. This is affecting both the posting of the slides and the textbook, so patience. They're all there. They'll appear at some point. Lecture 24, announcements. First announcement, we're back to homework mode. I just want to remind you that we have, just for sanity, made everything due at 7 p.m. rather than some things at 5 and some things at 7. Regrade requests, the tutors would like some sanity here, and so regrade requests are due the Friday of the week when the homework grades are released, and they'll be released early in the week, so you have a few days to look and ask for regrade requests. What else is there? Project 2, next week, you are going to look at murder rates and the death penalty. And in response to numerous questions about are there courses in data science, what can I take, etc., 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 I posted on Piazza about what to learn. If you want to learn more methodology to use in a domain, or if you actually want to become a data scientist, which is a slightly different approach. As we know more about majors and minors and courses and so on, we'll update you. Any administrative questions? We're sort of back in normal mode, labs, homeworks, etc., 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 and hope we will stay this way until the end of the term. Okay. So recap, our main business has been estimating an unknown parameter in your mind you should fix. There is a number associated with your population that you don't know. A parameter is a single number, not a set of numbers, but a single number. You're trying to estimate that. Your data at hand are a random sample from the population. Based on that, you get one estimate, but you know that it could have been different because your sample could have been different. So you somehow want to use that sample to see how different the estimate could have been. And so you will end up with an interval of estimates. This interval is called a confidence interval, and it has a confidence level, a 95%. Based on the same data, a 95% confidence interval is simply wider than a 70% confidence interval. And we went through how to create these things. Our method of creation is using the bootstrap method. You're trying to find a number in here. You can't see it. What you can see is a large random sample from here. That'll look kind of sort of like this by the law of averages. You can generate other random samples from this. All of these look kind of sort of like this, which looks kind of sort of like this with high probability. So you should be able to devise a method that produces a good interval a high percentage of the time. The method that we are using is the simplest of all bootstrap methods to get confidence intervals. If you go further into the bootstrap, you will see that there are many different ways of using the bootstrap. We are doing the simplest possible one. It is called, for obvious reasons, the percentile method. To get the 95% confidence interval, you take the middle 95%, which is the same as taking the 2.5th percentile and the 97.5th percentile. So all of this is just a rehash of what was done last time. Questions, commentary, etc., before we get to examples? So far, so good? Okay, let's see. So what I would like to do is go to... Okay, so here is our usual definition cell. Okay, take a look at this. Bootstrap median was a function that we defined, yes? 2 times ago, I think. So what I'd like you to do is look hard at the definition of the function because we have clones of this. Last time we had a clone that was bootstrap mean. Yep, and we'll do another one today to use in a different context. What I'd like you to do is actually look hard at the definition of this function because I would like you to be able to go away. About a week from now, I would like you to be able to go away, sit at a cafe with a pen and paper, no computer, and write out the definition of such a function. So for this, we need to look at the bits. And I'd like you to look at this red bit. There's a lot of talk. That's what it is, talk. It's comments to just remind us what the thing does. That is not code. So the heart of the function is this def statement here, the body of the function, and then the return statement. Return statements are associated with def statements. Okay, so the bootstrap median takes 3 arguments. Now, these names don't have any intrinsic meaning outside this cell. They are just generic placeholders. You could call them Bart, Lisa, and Maggie. So they exist only inside that cell, and they're just basically, this is telling you, this is oomph. Whatever is the table containing the sample that you want to use, that's the name that you have to enter. You will not enter this name ever unless you have for some reason called your table that. All right. And so here, what I'd like to do is I'd like to go through line by line why we are doing every step. So this is our table containing our original sample. We are selecting out the single variable that we are interested in. The reason for doing that is to make a big table into a small table. Right? A big table might have 17 different columns. We don't want to work with 17 columns. We want to work with one variable. So we first extract that. That just speeds things up a little bit. We know that we are going to collect sample medians, so we make an empty array in which we are going to collect them. This name, medians, is our choice. Right? We could call it Tyrion Lannister. It doesn't matter. But it's our choice because when we go back and read our code, if it says Tyrion Lannister, we won't have any idea what it's saying. So we chose to call it medians. Okay, and now there is a for loop. Now we are going to do something over and over and over again, and that's why there's a for loop. Yes? I haven't come to that yet. Hold on. So when you try to do something over and over and over again, you write a for loop. A for loop has your for statement on top, which gives you essentially the number of times you're going to do this. And you are going to perform this body for every element in this array. And there are going to be as many in that array as you choose to put up here. So notice that there's a for statement and there is a body. I want you to notice something. At the end of the for statement, there is no return. This return corresponds to this def. Right? The for statement just keeps doing this body over and over again until it exhausts all of these elements in the array. Okay, so now, the column that we reduced our original table to is a sample to start with. From that, and that was this question, this sample is a sample with replacement. The sample that we draw is a sample with replacement. The sample that our original table was could have been a sample with replacement or without replacement. But we draw a sample to do the bootstrap, so we sample with replacement, and we sample as many times as there are elements in this column, and that is why we are just using the defaults of sample, which are both with replacement sampling and sample exactly the same number of times as you have rows. Okay, so now we have our bootstrap sample, and this is an array, this is a table of numbers, and we use, this is the calculation of the statistic. So when you change the statistic, that is the line that will change. Everything else, only the names will change. We calculate our statistic, which in this case was the median, and for this you have to remember how to calculate a median. And there are two ways of calculating a median. You have percentile 50 array, or you have np.median array. You can use either. I'm using percentile 50 because when I ask you to bootstrap the 60th percentile, then you can use percentile 60. All right. And then this is just you make your array bigger and so on. So at the end of this, medians is a long array containing these many medians. At the end of all that, the function returns that array. What function? Bootstrap median. Okay, I've gone through this in gory detail because I want you to be confident with the different aspects. So what I'd like you to do, we've given you a Python playground. Copy paste this over, read in the table of data and run the code, then change all the names. Right? Change all the names to your favorite names. Define the function again, run it, and you should see the same output. Okay, so we have bootstrap medians, and then we have bootstrap mean, and I'll remind you of our data. This is a sample of 1,174 mother-baby pairs, and we did confidence intervals for the median ratio, birth weight to gestational days. We did a confidence interval for the average age of the mothers in the population. What I'd like to do is a confidence interval for the proportion of the mothers who smoked. And so if I look at, in the sample, what proportion of mothers who smoke, there are a number of ways of figuring out that proportion. Take a look at this code here. I've just used an array method just for the sake of using an array method. You could, of course, use .where and count rows. So the first thing we've done is we have extracted this column as an array. You okay here? .column extracts an array. This column consists of booleans, true and false. Right? You recall that false is 0 and true is not. So what we're going to do to count the numbers that are true is we're just going to count non-zero. To convert that into a proportion, we are going to divide by the length of the array. Good? Okay, so when you do these things, it is important to stop at every stage and ask yourself, before I type the next dot, what have I got at this point? Do I have an array? Do I have a table? Am I using the right kind of technique on that object? Okay, so in the sample, 39% of the mothers were smokers. And there's a question to, does that reflect the population, or is there a different number in the population? So you can use this to estimate the, you can use your sample to estimate the number in the population. And for this, we will define the function bootstrap proportion. What are we going to do, after all? We have 1,174 trues and falses. Yep? We're just going to sample 1,174 times at random with replacement from that list. We're going to get a different 1,174 trues and falses. That will have its own proportion of trues. That's going to be our first bootstrap replication. Then we're going to do that over and over and over again. Yep, that's the plan. So for this, we need the corresponding function, bootstrap proportion, takes the same arguments. It returns bootstrap sample proportions, not means, not medians. Something to note. It is assuming that the column that you're interested in contains booleans, because we're going to count the number that is true. And so same code as before, extract the column that you want into one column, create an empty column in which to collect your results, bootstrap your sample just as before. And now just to make some writing shorter, I have extracted the relevant column, and I'm doing np.count non-zero of that array divided by the length of the array. This gives me the proportion. I append the proportions, and the function should return the proportions. I'm going to shut up and have you read that. With practice, what you ought to be able to do at every stage is first remind yourself you are not going to read from left to right. You're going to read this side first. This is the action, and then it gets assigned to this name. Okay? Every time you have an action and you see a dot, ask yourself, what's on this side? That thing is a table. You apply dot select to it. What must this be? This must be a column label. What will you get as a result? You will get a table. All right? So please, every single time you do an operation, ask yourself, what am I getting here? All right. So read and questions, please. Okay, so this, takes a while to get used to it, but you have to make yourself do it, which means you have to make instead of reading the textbook like a novel, You have to actually use that Python playground and mess around. Okay, so I will define the function, and I will capture 5,000 bootstrapped proportions in an array called bstrap props, and I will compute a confidence interval. Take a look at this. What percent confidence? What's the confidence level? 95%, because I'm clearly doing 5% on the two left out, 2.5% on either side. Okay, tip, these two should add up to 100. Yes? Okay, and so our confidence interval for the percent of smokers among mothers in the population is essentially 36% to 42%, roughly. Yep? The percent in our original sample was about 39%, if you recall. It's right here. Yep. Notice that that is almost exactly halfway in between those two numbers. So no big surprise. You are, after all, bootstrapping from that sample. So that has some of the samples will come out with proportions bigger than that. Some will come out with proportions less than that. But, in general, they will be around that. So our sample proportion comes out to be somewhere near the center of that. Not exactly, but somewhere near the center of that. And we go from 36 to 42. What does that 36 to 42 mean? We are saying that we estimate the proportion of mothers in the population who smoked during pregnancy to be somewhere in the 36 to 42 range. That's what we're saying. Our process gives us a good answer about 95% of the time. I do not know a way to make these sentences shorter. Okay, so I'd like to remind you of something. Actually, why don't we visualize? This is a histogram of all 5,000 proportions that we got, and that's our interval right there, the middle 95% interval. Okay, do you notice again that? Yes, over and over again, you keep seeing these curves come up from nowhere. Next week will be spent discussing what's going on there. But for now, just notice there's a shape. Okay, I just want to recall a calculation we did last time. This set of 1,174 ages had a mean of about 27 years, and we estimated the mean in the population by running bootstrap means. I'm just going to redo that. And it takes a while, and the mean in the population was approximately 26 and a bit to 27 and a bit, 26.9 to 27.6, roughly. So I have... Actually, I'll come back to that. I want to ask you this. So this sentence is a summary of what the calculation that you just saw. Yep, that's the confidence interval we got. And I have a true-false question for you. Talk to your neighbor, please, and sort this out. All right, so there's an interval, and there's a 95%, and there's a 95% of something does something, and I just want to be really clear what it does and what it doesn't do. If you look at this statement, how many votes for true? Okay, a few very shy votes. How many votes for false? More. How many votes for I won't vote? Yeah, okay. Right. So what I want you to do is forget that you know anything about confidence intervals. Right? Forget that you've been in a class that does the bootstrap. Forget everything. Think about 1,174 mothers in the sample and many more thousands in the population. These are mothers giving birth in a hospital system. Yep? You are looking at the ages of those mothers. If you say that 95% of them have ages in this range, is that a big range or a small range? That's a teeny, tiny range. You're saying that 95% of them were essentially twins. There has to be something wrong with this sentence. It just can't be. No amount of theory is going to make that a good sentence. Okay. So that is a bad sentence, and we will see very specifically, graphically, why it is bad. What is important to understand is what does this interval actually do? All it does is estimate the average age. The average age is around 27. That's all it's saying. And to visualize what's going on, if we go back, we can draw a histogram. Let me give myself a cell here. So if I do baby.select maternal age, that was the sample of ages, and if I just do the histogram of these ages, these are the ages of the mothers in the sample. What do you think the distribution of ages of mothers in the population looks like? Like that. It's a big sample. You know, you have this trust that it looks like the population, unless you have been significantly unlucky. All right, so now you look at this. Where's 27 here? 27 is kind of somewhere here. Yes? So 26 and a bit to 27 and a bit is kind of here. Does that look like 95% of the people? It certainly doesn't. The women go all the way in age from 15 to 45 in the sample. You expect an even bigger spread in the population. That interval that you have constructed, all that it is saying is that your average is somewhere here, in this teeny, teeny, teeny little interval, 26 and a bit to 27 and a bit. You're just guessing the average. It's not doing anything else. Okay? So resist the impulse to use it for everything under the sun. I am sorry to let you know that large numbers of people in the world do use confidence intervals for everything under the sun and therefore are surprised when their results don't make sense. But the confidence interval is trying to do one very specific thing. There is one unknown number in the population. It's trying to estimate that number. That's all it's doing. We will see that that estimation actually leads to something powerful in just a moment. But it is important to be conscious that it's just estimating one parameter. Okay. Let me go back to a slide that I skipped over. So this bootstrap is a wonderful thing, and it's very powerful, but you shouldn't always use it. Okay. There are places where it fails, especially the percentile method that we have described. So recall that we have estimated means and medians and so on. Do you remember when we talked about random sampling, we said that random samples have difficulty picking up rare elements in the population? Yep. The proportions out in the tails are often quite far off from what they ought to be. So any parameter that depends on rare elements in a population, you are going to have trouble estimating. You're actually going to have trouble estimating with any technique, but you're also going to have trouble estimating with the bootstrap. So what depends on a rare element in the population? The extremes. Min and max, there's often exactly one of them, right? Almost certain not to show up in your sample. So we will mess up trying to estimate min and max. You will mess up trying to estimate the 99th percentile or the first percentile or something. All right, so if you are working in the bulk of the data, that is reasonable for this method, but you should not be working where, rare items in the population affect what you're trying to estimate. The method that we have used, this symmetrically, if I want 80% in the center, I'm going to leave out 10% here and 10% there. This is justified because if you have a symmetric distribution of your statistic. So if the distribution of your test statistic, and you see every time we've used it, the statistic has come out looking something like that. If it doesn't, especially if it is skewed on one side, you might have trouble. And so how do you know? You just look at your empirical distribution. If it is not bell-shaped, just pause for a second and say, I'll get a confidence interval, but its coverage might not be that great. And you should not use this method if the sample size is very small, and by very small, I mean really very small. Less than about 10 or 15 or so, you should start worrying. There are other methods you can use to correct, but we're not going to get into that in this course. Maybe in Stat 28, the next course, you will see some of that. All right, so the moral of this story is don't go too crazy with the bootstrap. All right, so what I want to do is I want to spend the rest of this lecture talking about a particular use of bootstrap confidence intervals to test hypotheses. And the use is very natural, and it's just a very nice thing that it happens to work. So I want to go back to this confidence interval. This is an approximate 95% confidence interval for the ages of the average age of the mothers in the population. Okay, supposing I want to test the following hypothesis. Actually, I type in the hypotheses. Why not? Never try to type the words average and age one after another. Both of them have age in them. It's very confusing. Supposing for some bizarre reason I want to test that pair of hypotheses. Take a look at your confidence interval. Which one of those two would you prefer? Null or alternative? Alternative sure looks good. Yes, our interval does not contain 25. And in fact, there is a very nice little piece of mathematics that says there's a duality between these hypotheses and your confidence interval. If you are testing the average age is equal to some x versus the average age is not equal to some x, and you use the 5% cutoff for the p-value, that is the same as making the 95% confidence interval that we just made and looking to see if your x is in there or not. So this gives you a quick way of testing hypotheses. You just stare at your confidence interval. If the value in your null hypothesis is not there, then reject the null hypothesis. If the value in the null hypothesis is there, so for example, if I change this to, how about 27? Now what? If you had to pick between the two hypotheses, the null doesn't look unreasonable, does it? Yep. So you would say, I don't have enough information to reject the null. I'm not going to reject the null. The cutoff for the p-value and the level of confidence are complementary. 5% cutoff for the p-value, use a 95% confidence interval. 1% cutoff for the p-value, use a 99% confidence interval. 3% cutoff for the p-value, use a 97% confidence interval, and so on. Now, one of the good things about this method is it doesn't just say, was it so if we do 30 versus not 30, I will end up concluding not 30, yes? But one of the good things about this method is it doesn't just conclude the average age was not 30. It actually tells you, I think the average age was in the range 26.9 to 27.6. So it tells you what it was rather than simply what it wasn't. Yep? So it is more informative. In that sense, it is a better method to use than simply testing hypotheses. Yes or no. Now, a number of you, I hope, have asked the following question in your head. Why would I even ask this question? Why would I ask, is the average age in the population equal to 30? That's so bizarre. What's special about 30? And in fact, you typically wouldn't. But there is one number which often is very important to test whether an average is 0 or not. And so what we're going to do next is we're going to use exactly the methods that we have developed to construct a confidence interval in a situation where exactly this kind of test becomes very important. And the example is in the context of a study on Hodgkin's disease. Hodgkin's disease is a cancer that affects relatively young people in their 20s, though, older people can get it as well. It's a cancer of the lymph nodes. And about Hodgkin's, there is the good news and the bad news. The good news is that it's curable. The bad news is that the treatment is extremely harsh, and people suffer during the treatment and for quite some time after the treatment just from side effects of the treatment. The tumor goes away, but other stuff suffers. And so the purpose of this study, and it was very well randomized and so on, the purpose of the study was to see what is sort of the minimal dosage configuration that you can give someone that will A, get rid of the tumor, but B, not damage the patient too much just from the treatment. That was the goal of the study. And so I'm not going to give you this is a very small subset of the data. Each row corresponds to the patient's. This is your first not massive sample. Yeah, there are 22 people in the sample. Each row corresponds to a patient. The size of the patient is important. What is happening is that they get radiation, that's the second column, the amount of radiation, to what is called the mantle, is the chest area. There's a dose of chemotherapy, there's bleomycin, there's a bunch of drugs that are given combination. And what is measured, this is a baseline value, is called forced expiratory volume. You can just think of that as a measure of how much people can blow into a paper bag. Higher scores means their lungs are more healthy. So patients are measured at baseline before the treatment. And then they are measured again 15 months after the treatment. All right, so I want you to just pick your favorite row from that table and just imagine that is one patient. You know how tall the patient is. You know some measure of dosage, radiation and chemo. You know how well the patient was able to blow into a bag before they got the treatment and how well 15 months after the treatment. You can assume that the patient was cured, right? What we were trying to do is, I say we, I was involved in this, is try to see, how bad was the effect 15 months after the treatment and then, 3 years after the treatment. Does it go away? And so if I look at these numbers, it sure looks like people are doing worse 15 months after the treatment. You agree? In general, the scores just seem to drop. They're not doing as well. And a natural quantity to measure then is how much was that drop. So what we've done is we've just augmented this with the drop from baseline to 15 months. The positive drop means it dropped a lot. The negative drop means it actually went up. Yep? And I'm looking at that, and virtually every one of those is positive. You agree? There's a few that are negative, but in my group, most of them are positive, so most of them are suffering. And in fact, if I look at the histogram of the amount of drops, no drop is here. Right? You can see the majority had a positive drop. And it's a minority that did better after 15 months. You all agree? That's what the data are showing us? So we could stop here and say, well, at 15 months they're doing worse, but as data scientists, statisticians, we have to remember that this is only a random sample of 22 patients. Maybe if you look at the entire population, in the population, the average of the drops is actually 0. Could be. Yep. And so here is a place where you are actually interested. In the sample, the average drop was 28. Here is a place where you are actually interested. The average drop in the population is 0. The average drop in the sample is due to chance. Versus, now, in a medical study, you cannot presuppose your results. You have to have your null and alternative set up before you run your experiment. Therefore, the only reasonable assumption, alternative that you can set up is the average drop is not 0. Because you'll have set this stuff up before you get the data. Right? Invariably, almost invariably, in a medical study, the alternative is going to be two-sided. The treatment does nothing versus the treatment does something. We're not saying what. Okay? So those are the two hypotheses, and I want you to look at the nature of the hypothesis. It's about a population mean, and you're saying that the population mean is equal to a certain value, which was exactly the same as what we had here. We had a population mean, and we were saying that it is equal to a certain value. Yep. But what we're doing now is a little more natural than asking whether an average age is equal to, 29 or whatever it was. Okay. So we now have a method to carry out such a test. We have a list. We have a sample of drops. Yep. From this, we have one estimate of the average drop in the population. That estimate is about 28. That's what came out. How would you go about getting another estimate? Bootstrap that sample, get another sample mean. Yep. Do that again and again and again and again. Get a whole bunch of sample means. You can construct your interval of estimates for the population mean. Does that sound like a plan? So before we execute, we have one sample of 22 drops. That has one average. Yep. We're trying to say something about the average in the population. So we need to know roughly how big we think that is. And the way of knowing how big that is to construct a confidence interval. A confidence interval for what parameter? So anytime I say parameter, the first word you should say is population. So you are going to construct a confidence interval for the population mean. You're trying to guess the mean drop in the population. Terrific. Why don't we select a cutoff for the p-value? How about I'm tired of 5%. Shall we do what medical professionals do and just use the 1% cutoff? Yep. We'll do 1% cutoff. We'll get a nice big confidence interval. Okay. So we have to get a bunch of means for which we are going to use what function? It's one of the ones that we define. It's called bootstrap mean. Okay, so we are going to use bootstrap mean. The table is called Hodgkin's. The column is called drop. I'm doing 10,000. Why am I suddenly doing 10,000, not 5,000? Because I have such a tiny sample, 22, that bootstrapping is not going to take any time at all. So I might as well just do as many. I could probably do 20,000. All good? Then I have to find the middle 99%, right? This is a pain. The middle 99%. So I'm leaving out a total of 1%. Yes? on the left-hand side, what percent am I leaving out? 0.5%. Okay, so therefore my left end is going to be percentile number 0.5 of this. Yep. And the right end is going to be 100 minus that. All good? And then we are going to take a look. All right. So before I run, questions? Ready to run? Any questions? Chugging, done. And the confidence interval goes from approximately, so this is a confidence interval for what? We are estimating the average drop in patients in the population. And we think that's between 17 and 40. What was the hypothesis? The average drop is 0. That was a null. The alternative is average drop is not 0. Which one are you picking? You're picking the alternative, yes? What's your cutoff for the p-value that you just used? You used 1%. All clear? You understand how to use this method? And the great thing about this method, compared to other methods of hypothesis testing, is you don't just go away saying, no, the average drop wasn't 0. You say, on average, the patient dropped between 17 and 40 points. That's very helpful. Now you have some sense of how bad the effect is going to be. Okay, so I have a couple of endnotes, the first of which is, notice how wide this interval is. Right? We haven't had such a huge wide. This is 17 to 40. It's well over 20 units wide. Right? There are two big reasons why it's wide. The first is we chose to make a 99% interval. That's going to be wider than our 95% intervals. You agree? Middle 99% is just a bigger range than the middle 95%. Okay, that's one. What's the other reason? Sample size. We got a tiny sample. Our estimates are not going to be sharp. Right? They're going to vary all over the place. Exactly how sample size affects variability, and from where we get these bell-shaped distributions popping up at all times, is going to be the subject of next week. But the thing that I want you to look at is if your sample is relatively small, your confidence intervals are going to be wide. If your sample is huge, only then do you have tight estimates. So accuracy doesn't come cheap. And exactly how big of a sample you have to take to achieve a certain level of accuracy, we'll talk about next week. Okay? All right, so one more note. I had said when I introduced the bootstrap that it was introduced, the method was proposed by Brad Efron, and I think he was born in Minnesota. He's used an American expression from to pull yourself over the fence by your own bootstraps. And that's very evocative because it says when you don't have a tool, just look around, see what you got and use that. So that's exactly what's happening here. We've only got one random sample. We're trying to say something about variability in sampling estimates. Let's just use the one random sample that we have to generate more random samples. Very evocative if you understand what pull yourself up by your own bootstraps means. Now, idioms are very culture dependent. And so these names that were used during the 1990s, the bootstrap, the jackknife, ace, Mars, cart, there were all kinds of names. They were all coming from the United States, actually all coming from the two Bay Area universities. They started to tick other people off. What is these Americans coming up with all these names that are now inflicted on the rest of the world, and everybody has to understand this stuff? So other people decided, okay, we can do this too. Here we go. Come on. Title of paper is, do I have a Chinese speaker within range of the microphone? Anybody can read out what that means? But she's looking at it, okay, this is not something you recognize? Is there any Chinese speaker in this room that recognizes that expression? I, as a non-Chinese speaker, am happy to tell you what it means. It means throw a brick and get jade. Now can you say what it means? Somebody try and read it out? I'm going to hand them the mic. In Chinese. Oh, here we go.
Thank you. 抛砖引玉.
Again.
抛砖引玉.
Okay. So that's the name of their method. Throw a brick and get jade, which means, do something rather crude and get a terrific result. And so one of the reasons I put that up there is to say that other cultures can make names too, but the other reason, the main reason I put that up there, is for you to read the first line of the abstract. Okay? This is a paper in the 1990s proposing an improvement on the bootstrap method, or a version of the bootstrap, the method of something that I can't pronounce because it really matters how you sing these words, introduced by James Fu and Lungan Li, is now we're going to read these words, data-based, computer-intensive, resampling technique, sounds familiar? Which provides a numerical solution for the minimum variance, unbiased estimate. You see, minimum variance is a good thing. You want tight estimates. Unbiased means that on average you want to get to the right point. Unbiased estimator of a one-dimensional parameter, that is a single numerical parameter. That's exactly what you're doing. Right? Now you have got to what you can do without the mathematical basis. Of course, this paper was doing all the mathematics, but notice that it is entirely possible to understand the motivation for the technique and actually carry out the technique without several 15-week edifices of mathematical courses. So when we set out to teach you this stuff, and we said we were going to teach this to freshmen who had no background whatsoever in these fields, all our expert colleagues at different universities told us flat out it's not possible. It's possible. You've got it. All right, I'll see you Monday.